Today we are going to cover the chapter 6 of our book. That's the properties of the dry gas reservoirs. Uh, as we discussed last time, the dry gas reservoirs are the easiest reservoirs to deal with because we will not have the liquid. The petroleum fluids will stay in the gas phase throughout the production, and it will stay gas when it comes to the surface. So the composition of the gas will be the same as at the surface will be the same as the composition of the gas at the reservoir. So we can simply take the sample from the surface and then send it to the lab and do all the measurements that we have discussed before. So in this session, what we are going to do, we are going to study the three main properties of the dry gas reservoirs, and that's the gas formation volume factor, coefficient of isothermal gas compressibility, and the gas viscosity. Okay, and two of these properties will be your open book question for the midterm. So what is the gas formation volume factor? We discussed this before. So the gas formation volume factor was the volume of the gas at the reservoir condition divided by volume of the gas at the standard condition, which is like if I have 1 barrel of, if I have 1 standard cubic feet of gas at the reservoir, one how much of the gas I can produce at the surface, basically. That's definition. So the gas formation volume factor is shown by Bg and is defined as VR over V at the standard condition. Okay, so the dimension can be reservoir cubic feet of gas per standard cubic feet of gas. Okay, or we can convert that to reservoir barrel per standard cubic feet of barrel. Okay, and the conversion factor is 5.615. So 5.615 cubic feet per barrel. We can use that to simply convert the dimensions. Sometimes people report the BG in reservoir barrels per standard cubic feet of gas. Okay, and 1 over the standard cubic feet of gas, also called the gas expansion factor. Okay, so if I write the compressibility equation of a state, so uh, then I can change this Bg. I can write the Bg that was VR over Vsc, volume of gas at the reservoir divided by volume of the gas at the standard condition. I know PV is equal to Z and RT, so V becomes Z and RT over P for both conditions. Then N, the number of moles, is the same, so I can cancel that out. R is a universal gas constant. I can cancel that out. So the equation will simplify to Z T PC over Z standard condition, temperature standard condition, and the pressure. At the standard condition, the Z is 1. Okay, we assume the Z at the standard condition, the compressibility factor is equal to 1. We know the temperature at the standard condition, 60 degree plus 460 because 520. We know the pressure at the standard condition, that's 14.65. So the BG becomes actually 0.02282 ZT over P. Okay, so the gas compressibility factor becomes equal to a constant, which is 0.0282, times the Z factor at the reservoir condition, temperature at the reservoir condition, and pressure at the reservoir condition. As I said, we can convert this to reservoir barrel per standard cubic feet by simply dividing that by 5.615. So if I divide this by 5.615, cubic feet goes by cubic feet, then I will have the reservoir barrel per standard cubic feet of gas. And that becomes Bg is equal to 0.00502 ZT over P. Okay, so depending on the question, if you want to report the Bg in reservoir cubic feet per standard cubic feet, this is the equation that we are going to use. Bg is equal to 0.0282 ZT over P. And if the question asks you to report the Bg in reservoir barrel per standard cubic feet of gas, then you divide this number by 5.615 or simply use Bg is equal to 0.00502 ZT over P. So in this example, we can see the temperature of the reservoir we usually know. The pressure is given. The only unknown to find the Bg is the Z factor. And generally, for the Z factor, the composition will be given. This was our discussion last week. So the composition was given. And if you are interested to find the Z, you need to find the pseudocritical temperature, pseudocritical pressure, If you have non-hydrocarbon components, you need to correct the pseudo-critical temperature and pressure, and then you need to find the pseudo-reduced pressure and pseudo-reduced temperature, and then from there you can find the Z factor. So finding the Z factor, which was the discussion of the last week, is the major part for the rest of gas properties calculations. So how the BG is changing as a function of pressure. So at a high reservoir pressure, the BG is small, okay? And as we go to lower pressure, because of the gas expansion, the BG goes up exponentially, okay? Remember, the BG was volume of the gas at the reservoir divided by volume of the gas at the standard condition. At the reservoir, the pressure is higher, so the volume of the gas is not going to change that much, but the volume of the gas uh, at the reservoir condition, when the pressure is high, the volume of gas is smaller, but as the reservoir pressure goes down, the volume of the gas becomes larger because the gas expands. So that VR goes up, and then the BG exponentially goes up. Okay. Okay. So let's do an example. It basically says calculate the formation volume factor of the gas. It's in terms of reservoir barrel per standard cubic feet. When the gas specific gravity is given, that's 0.818, and reservoir temperature and reservoir pressure is given. Okay. So in this case, the gas composition is not given. So if the gas composition is not given, we learn in chapter 3, with the gas specific gravity, we can find the critical pressures and pseudo-critical pressures and pseudo-critical temperatures, and from there we can find the reduced pressure and temperature and the Z factor. So the first step is to write the equation. Since the question says the BG needs to be reported in reservoir barrel per standard cubic feet, so the BG becomes 0.00502 ZT over P. The temperature is given 220. Remember, we need to add 460 to convert that to Rankine. The pressure is given in PSIG 2100, so we need to add 14.7 to convert that to PSIA. So the only unknown is the Z value. Okay. As I said, since this is the gas specific gravity is given, we can go to figure 311, and from there we can read with the specific gravity given, I can read the pseudo-critical temperature and pseudo-critical pressure. When I have these two, pseudo-critical pressure and temperature, then I can find the reduced temperature and reduced pressure. And simply by dividing the pseudo-critical temperature by the reservoir temperature and pseudo-critical pressure by the and reservoir pressure divided by pseudo-critical pressure. Okay, so reservoir temperature divided by pseudo-critical temperature and reservoir pressure divided by pseudo-critical pressure. Then we can have the TPR and PPR. So the PPR is 3.27 and TPR is 1.68. So 3.27 for PPR and 1.68. So 3.27. So we know the PPR is less than 8. So pseudo-reduced pressure is less than 8. So I use the upper part of the Z chart. And then I go to the PPR. Then I draw a line to 1.68. That's the TPR. And I read the Z value, which is like 0.85. Okay. So I got the Z value. Then I can plug in and I can find the BG value. So I have the equation. Now I have the Z, temperature I know, pressure I know, and I can find the BG value. But as I said in the class, most probably what you will have is the composition of the gas is given most of the time. Okay. So here the question is to find the coefficient of the isothermal gas compressibility. That's basically the second property that we are interested. So the gas compressibility is defined as 1 over volume times the change in the volume as a function of pressure. Okay, it could be 1 over molar volume times the change in the molar volume as a function of pressure, or it could be 1 over specific volume times changing the specific volume with respect to pressure. Okay, so these are basically equivalent terms. And as you notice, the unit of the compressibility is 1 over pressure, because the volume, the volume will cancel out and I have only pressure. Okay. So the gas compressibility factor is also changing, very similar to the BG, to the gas formation volume factor. At a high reservoir pressure, gas is compressed, so the change in the volume with respect to pressure is less. But as we go to the lower pressure, that change becomes more significant. Okay. So sometimes in the lab, you will have the luxury of measuring the molar volume as a function of pressure. Okay, for example, here at different pressures from 700 to 800 to 900 and to 1300, the molar volume of the gas has been measured. Okay, in this case, it's very easy to find the gas compressibility factor at any pressure range. Okay, and the way it works, we write the equation for the gas compressibility. Here, the molar volume is given, so I use the equation that's based on the molar volume. That's minus 1 over molar volume times the change in the molar volume as a function of pressure. So if I'm interested to find the gas compressibility at 1000 psi and 150 degree Fahrenheit, so at 1000 psi, the molar volume is 5.7, so I have that. Now I need to find the derivative of molar volume as a function of pressure at 1000 psi. And for that, I can simply plot the molar volume as a function of pressure. And we know the derivative is the slope of the line at that pressure. So I go to 1000 psi, and then I draw the tangent to the curve, and I find the slope. So the slope of the red line, which is a tangent at 1000 psi, because the question was to find the compressibility at 1000, is giving me dV over P. So the slope of the line, I can find the slope, and then when I have the slope, I plug into the equation and I get the gas compressibility. Remember, the gas compressibility dimension is 1 over pressure, so it's per psi. Okay. However, in order for equation 6.4 to be useful, it must be combined with an equation of a state that relates the pressure and temperature and volume, because I want to eliminate one of these components from one of these terms from my equation. Okay, so if I use the ideal gas equation of a state, then that's simply PV is equal to nRT. Okay, or volume becomes nRT over P. In this equation, I know the mole of the gas is not going to change, the R is not going to change. The experiment is done at a constant temperature, so the temperature is constant. So V is basically equal to a constant over pressure. Okay. So in that case, if I take the derivative of the dV over dP, okay, and RT is constant, so times the derivative of constant times pressure is 0. The derivative of minus the derivative of denominator times denominator becomes minus nRT over denominator squared. So now I have this derivative term calculated. I can replace that into the equation. So again, V is nRT over P, and then dV over dP is minus nRT over P squared. And then if I plug that in, nRT goes with nRT, P goes with P, then I have 1 over P. So in the case of ideal gas, isothermal compressibility for ideal gas, the gas compressibility is simply equal to 1 over pressure. Okay, so what is the gas compressibility at 1000 psi? That's 1 over 1000 psi if you assume ideal gas. However, this is simply an example. However, if we assume the gas is not ideal and the gas is real, then we know the PV is equal to ZnRT. Again, N is the number of mole constant, R universal gas constant, T is measured, the gas compressibility measured as a constant temperature, so it's constant. However, this time Z and P, they both change as a function of pressure. Okay, so in the next part of the lecture, we go over this equation to be able to find the dV over dP as a function of Z compressibility factor and the pressure, and see how we can apply that for the real gases.